Okay, welcome back. We are going to do the 7.7 part. That is the exponential growth and decay. Um, Basically, you're going to use the exact same formula that we used before. The y equals a times b to the x. That's the formula for an exponential function. And you're going to apply it to when population or money or anything grows by a percentage. So, those last few word problems we did in the previous lecture dealt with, um, you know, it increased by, it tripled or it doubled or it quadrupled. It increased by a factor, or, it was cut in half, or it was, it decreased by a third. So when it deals with those types of numbers, you can just do the method we did before. A, your initial value, B, whatever your factor is, X, whatever your amount of time is. But what if you're given a percent, since the population has grown by 3.5% annually? Or, you make 6% annually interest on your savings account, something to that effect. You're going to deal with exponential growth or exponential decay. Growth obviously being if it's something that's increasing, growing, gaining, anything like that. Decay being anything that's decreasing, lessening in value, anything of that sort. Now, they are basically done the exact same way. It just is a matter of what your B value becomes. Now, what you need to do is you're going to set it up just the exact same way, where A is your initial value or what you start with, and B is going to represent your change or your factor. It's either going to be a growth factor or a decay factor. Now, the main difference is your growth factor, as you can see right here, if you can read it, it says it equals 1 plus the percent rate of change. So 1 plus percent rate of change for growth, and you can guess it, decay, if we scroll down a little bit, you can see will be 1 minus the percent rate of change. And so, in fact, I'll kind of leave it to where you can see it. 1 plus the percent rate of change. I'll just redo it. 1 plus the percent rate of change is your growth factor. 1 minus the percent rate of change is your decay factor. And so that's really the only difference. It's really not too bad. You're just going to plug in your initial value for A. You're going to take 1 plus the percent for growth, 1 minus the percent for decay as your B value, and then X represents the number of time that's elapsed. And so the only other caveat you have to do is remember that we are going to want our percents expressed as decimals. So to do that, you've got to move your decimal place or your percent symbol. So if we have 50%, you're going to want to move that decimal 2 places to the left. So 50% as a decimal is 0.5. And so 0.5 is what we're going to add to 1 or subtract from 1 to get our growth or decay factor. So we're just going to, I think the best way is just to kind of go by example. So we're going to do this first problem here. Suppose the population of deer have decreased or increased. So suppose the population of deer in a region was 3,500 in the year 2000. Since then, so since 2000, the population has grown by 3.5% annually. So it has grown by 3.5% each year since 2000. What will the population be in the year 2020? So we're just going to set this up. Y equals A times B to the X. Now, A is our initial value. Our initial value was 3,500. So Y equals 3,500. Let me type this, it'll be a little neater. So our 3,500 is our initial value. So this becomes y equals 3,500 times b to the x. Now we need to find this b value. Well, like I said, there's not a number. They give us a percent. And so if we move the decimal point in our percent 2 places to the left, 1, 2, we get 0.035. So our percent as a decimal is 0.035. So if you remember, as a growth factor, we are going to add that decimal to 1 to get b. So 1 plus 0.035 is 1.035. That simple, to the x. Again, I got this number by knowing that this is a growth factor. You see the word grow here. And growth factor, if you recall from up above, is 1 plus the percent change. So 1 plus 0.035 is 1.035. Now we need to find out this x. Well, that started in the year 2000. We want to know what it is in the year 2020. So how much time has elapsed? Hopefully you have seen 20 years. So we are just going to plug 20 in for x. And this will tell us what the population would be in 2020 if the deer population keeps growing 3.5% annually. So we pull up the calculator and we just plug this in. 3,500 times 1.035 to the 20th power. So you can see the deer population will be 6,964.2 deer. You can't really have 0.2 of a deer, but you want to account for that deer. So there will be 6,964 deer with one about to come, maybe one on the way. So right around 6,965 deer is what the population will be in 2020 if it grows 3.5% annually for 20 years. Okay, so we're going to do another example because, like I said, I think examples are the best way to go for this. This one deals with a decrease. So after this, we're going to do 2 more examples on a different worksheet, one of growth and one of decay, and then I'll show you compound interest and we'll be done. So this one, exact same concept, exact same situation. Y equals A times B to the X. That's what we're dealing with. So, let me over here. Okay, so we know that A represents the initial value. So here's the situation. The population of New Haven, so that's a town, was 148,220 in the year 2005. Since then, it's been decreasing at an annual rate of 2.9%. If this rate of decline continues, what will the population be in the year 2015? So right now, what will the population be this year according to this model? So let's plug in our values here. Now, I can't do the writing here, so I'm just going to do it over to the side. Y equals our initial value, which is A, which is 148,220 times my B value, which my B value in this case is going to be 1 minus my percent change because it is decay. So we move our decimal place 2 places to the left. So 1 minus 0.029. If you do 1 minus 0.029, you should get 0.971. And so if we put erase that other point there. If we put 0.971 to the x. The last thing we have to do, so this is the equation that can tell me what the population was in 2012, 2008, 2015, whatever. But we want to know what it is in 2015. So the number of years between 2005 and 2015 is 10. So we're just going to plug 10 in for x. So let's do that into our calculator real quick. 148,220 times 0.971 to the 10th power. That gives us 110,433.06. So right around 110,433. So that's what we're at. 110,433. Now obviously probably the easiest way to check your work with growth and decay is if your number is bigger than your starting one and it was supposed to decrease, you probably did it wrong. Likewise with growth, if your number is smaller than the initial and it was supposed to grow, you probably did it wrong. So again, I'm going to go to these other notes. I want to do a couple more example problems. You can find these on the handout that says exponential growth and decay. Now, we are going to use these to do review and such. It looks like this. For now, I'm going to do number 1, which is another example of growth, and I'm going to do number 8, which is another example of decay. It's not homework, but I highly, highly, highly encourage you to do as many of these as you can. I'm not going to post the key quite yet. I'll post the key tomorrow because we might use some of these during our review tomorrow. So if you want to hold off, that's fine. But let's kind of work through these here. So again, this is the exponential growth and decay link. We're going to do number 1. And so let's figure it out. Y equals A times B to the X. So it says find a bank account balance if the account starts with 100, has an annual rate of 4%, and we're trying to find what the money will be there after 12 years. So you're going to gain 4% each year. You're going to gain 4% each year. If you don't know how bank accounts work, when you put money in, it gains interest over years. This one is 4%. So that $100 initial starting value that you put in the bank, after 12 years, gaining 4% interest each year, we want to know how much money you'll have. So this is very applicable to you as a person. So let's see what that will be. We're going to set y equals to our initial value, which was 100, times our b value. And if you remember, if it's growth, you're going to take 1 plus your percent change. And so our percent is 4%. So as a decimal, that's 0.04. 1 plus 0.04 is 1.04 to the x. Now we want to know how many years, and that's what we're going to plug in for x. Well, you can see we want to know what it is after 12 years. And so if we plug 12 in for x, y equals 100 times 1.04 to the 12th power. Plug that into your calculator over here. 100 times 1.04 to the 12th power. That $100 will have magically turned into $160.10. So that will have turned into $160.10. So pretty nice way to figure out, if you've got a savings account, how much money you might expect just for leaving money sit there after 12 years of annual insurance. So you can make $60.10 of free money just by letting that $100 sit there for 12 years. So I mean that's good to see. One more growth and decay problem. We're going to go down here to number 8. This is obviously going to be an example of decay. This is another thing very applicable to your life. If you've ever taken medicine, you may have heard of something called half-life, and that's about, that's how the amount of medicine decreases over time in your body. And so, you know, just talking to your doctors when they say, well, it has a half-life of this or a half-life of that, you can feel more informed on knowing what that means by doing a decay problem such as this. So again, let's highlight our pertinent information. An adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases by 29%. Each hour, it decreases by 29%. How much ibuprofen is left after 6 hours? So again, let's set up our equation here. Y equals A times B to the X. Y equals the initial amount of ibuprofen, 400 milligrams, times our B value, which, remember, in a decay problem, and you know it's decay because the word decrease, you're going to do 1 minus your percent. 29%, if you move the decimal, is going to give you 0.29. 1 minus 0.29 is 0.71. So we would put 0.71 to the X. Again, the X is after 6 hours, so Y equals 400 times 0.71 to the 6 hours. And then so if you plug that into your calculator, 400 milligrams times a decrease by 29% over 6 hours will leave you with 51.24 milligrams of ibuprofen after 6 hours. So there'll still be a little ibuprofen in there. How much exactly? 51.24 milligrams of ibuprofen. So this is the example of growth and decay. I've got one more example to show you of a very specific type of growth. It's called compound interest. And I'm only going to show you the one problem. Now it's got a really long formula. There are 2 compound interest questions on your test. You are given the formula, so you don't have to memorize this formula. It's just something that you've got to be, familiar with using. So way at the bottom down here you see compound interest problems. There's 2 of them. We'll do both of them, and then we'll be done for today. I'll let you know what your homework is. So, compound interest. It's set up a lot like y equals a times b to the x. Y equals a times b to the x. It's just because of the term compound, and if you're unfamiliar with how compound interest works, I just want you to Google it really quick and do some just subtle research on it. It's not going to let me type. I don't know why it's not letting me type. But if you type compound interest, it would kind of be beneficial to see. Oh, that's why. My internet is all messed up. Let's try it again. Maybe it'll work this time. Compound interest. So, if you want to know kind of how it works, this is actually a decent article explaining it. basically, how compound interest works is just how it makes it sound. Your interest is kind of compounding. Most situations, like the growth and decays that we just did, they compound every year or annually. And so basically, that interest isn't being added on to that value until the end of the year. But there are some situations that deal with interest compounding um, more often, maybe every month or maybe every 3 months. And that is basically what differentiates compound interest from the other growth and decays. So you can read up on that if you'd like. If not, you can just trust me that this formula gets you there, because you could do this exact same formula for a regular growth and decay, because the number of times it compounds is once. And so your n value would be 1 each time here. And so you would be left with exactly what we just did with the growth and decay. The difference is this n value isn't going to be 1 because we're going to compound more than just every year, once a year. So A is going to be the balance, the amount of money left at the end. P is the principal. That is basically your initial value. How much money are you starting with, etc. R is the annual interest rate. So how much is the annual interest rate? That'll be the percentage that you're given in the problem. Whatever percentage you're given in the problem, that is what goes for your R value. The N represents the number of times compounded. And you're probably going to see one of two terms. You're probably going to see quarterly, or you're probably going to see monthly. So if it compounds quarterly, it's going to compound 4 times throughout the year. Quarter is 4. So that means every 3 months, your interest will compound. Monthly, it'll compound 12 times because there are 12 months in a year. So just keep that in mind. And T is the time in years, the number of years that you're let this interest accumulate. So let's just jump right in. Again, you don't have to memorize this formula. It is given to you on the test. I'm not going to expect you to memorize it. You just got to know how to plug the given information into it. So let's check a look here. Michelle invests $8,000 in a money market account that pays 3.25% interest compounded monthly. How much will be in the account after 12 years? So do not overthink this. Just take your time and go through it. An initial investment of $8,000. That's going to be your P value. The account pays 3.25%. That is going to be your rate. Compounded monthly. That is going to be your N value. After 12 years, that'll be your T value. So then you are looking for A. That's the question. How much money will be in there? What will be the balance after 12 years according to all this information? So then you just kind of plug it in. 8,000 was the principal or the initial. So A equals 8,000 times 1 plus. Now this is kind of like the growth problem. 1 plus the percent would be the growth, but now you've got to divide it by how many times it was compounded. So again, you're going to make your percentage a decimal. So that would be 0.035 over n. N is the number of times compounded. Well, this was compounded monthly, so it would be 12. And you're going to raise that to the power of n times t. Well, n was 12 times the number of years, which was 12. And then you're just going to go through and start simplifying all of this. So what I would do is just systematically do all of the parts on a calculator. And if you hear my son crying in the background, I apologize. He's, I think he's just waking up from a nap. So you've got to do all of this part first. The 1 plus 0.035 divided by 12 to the 12 times 12 power. So you could do I'll show you how I will do this. You take 0.035 divided by 12. So I did this part first, and then you add that to 1. So that gives me the entire parentheses, and you raise that to the power of, make sure you put parentheses up here, 12 times 12. Now, if you know that 12 times 12 is 144, you could just put 144, but you might be dealing with numbers that are bigger, and so I just do that. When you hit enter, that 1.521, that is all of this part here. All you simply do there is times by 8,000, and there you go. So that initial $8,000 investment, after 12 years, if it's compounded monthly at an interest rate of 3.25%, will be $12,168.25. So it seems complex, but all it is about setting up this formula and then make sure you don't mess up the calculation. So I want you guys to try this next one on your own. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? So go ahead and give this a try. Pause the video and try it. I'm going to go ahead and keep going so you can check your answers after you've paused it and tried it. So here's our information. They put $2,000 in there initially. That pays 4.5% interest compounded quarterly for 18 years. So let's set it up. A equals my initial investment, which was $2,000, times 1 plus my rate, which as a decimal is 0.045, divided by the number of times it was compounded quarterly. That means it was compounded 4 times. Put 4 here. All of that to the n times t power. N is 4 for 18 years, so 4 times 18. Again, I wouldn't try to plug all this into a calculator because you might mess up the parentheses somewhere. And so I honestly would do it the same steps I do it in the calculator. And that is, do the fraction first, 0.045 divided by 4. Take this answer and add it to 1. Take that entire answer and raise it to the parentheses 4 times 18th power. And then take that entire answer and multiply it by my initial investment, $2,000. So you can see that after 18 years, so when they graduate high school, just from putting that $2,000 in the account and not touching it ever again, when they graduate, they'll have a nice $4,475.53 account balance that they can use for college or whatever. So you can see that if you find an account that will pay a higher percent interest, and you put a higher initial value in there, you can increase the number of your balance, more efficiently or more quickly, or just after the same amount of time, it'll be much higher. So again, if you have any questions, shoot me an email. Your homework tonight will have some compound interest questions on it. Your homework tonight will have some exponential growth and decay, as well as graphing and writing exponential functions. So it's kind of hard. I fully expect that you guys will send me some emails if you have some problems. The homework and everything's listed on the announcements. If you want, I can write it right here real quick. It will be page 450 and 451, 9 through 29, every other odd, and page 459, 9 through 17 odds, 18, 27 through 29, and 33. So this is the homework. And if we have school tomorrow on Friday, I expect everybody to have this done. No excuses. If you struggle with it, you need to send me a Canvas message. I'll try to walk you through it, or work with a friend, or Khan Academy, Virtual Nerd, Google it. Use all these resources you have at your disposal. I think you guys can figure it out. Thank you for your time. Good luck. Again, do not hesitate to shoot me a Canvas message or an email if you have any problems. Thank you, guys.